thanks to Serena and First Mark for organizing this event. I'm Jonathan Grandperrin, CEO at Mindee. I don't have any slides on Mindee, but we are providing developers with solutions for them so they can extract data, text data on images and photos. And obviously, we are an AI company, and we do a lot of computer vision. So thanks to Serena, I said, because it's been a while, I'm passionate about computer vision, and it's been a while I wanted to think and to spend some time thinking about the whole deep learning history, the whole computer vision history. So that's the point of this talk today. I will not deep dive into each of these different steps, but I will try to give you an overall understanding of all the different steps that led us from nothing in computer vision to where we are today. And the use of amazing applications with deep learning and so on. So everything started in 1957 with the perceptron. The perceptron was the first artificial neuron. The idea, engineers love to get inspiration from biology and nature to create machines. For example, you can see on the left the first airplane that was crafted. It looks like a bat maybe, or a weird bird, I don't know. The gecko for his very sticky fingers. The DNA, because some optimization algorithms are based on evolutionary algorithm inspired from the DNA evolution, the human evolution, and so on. When it came to intelligence, the main idea was obviously to get inspiration from the brain, but the brain is way too more complicated to do something, to create a machine that acts like the brain. So Frank Rosenblatt in 1957 just used and get inspiration from what makes the brain a learning machine, the neuron, actually. A neuron works quite simply. It's only a bunch of signals. It takes as input a bunch of signals. Maybe, for example, the value in each pixel of an image. It weights, or it multiplies by a weight each of these signals, create the sum of the resulting weights, the resulting signal, and let the signal pass if it's strong enough. Otherwise, it blocks it. So a bunch of signals, each signal is weighted, then the sum of it, and that's it. That's how a neuron works, but how to learn it? That was the real question. The principle of learning and machine learning we use today and we have been using for the last decades to create deep learning algorithms and so on was inspired by neurons and how to weight it. It's only what are the good weights we have to put on the neurons so it can answer or predict an answer to a specific problems. In this example, the first artificial neuron is the picture on the right, and I think maybe it was just trying to solve a binary classification problem, like is the image representing a C character or something else? It was not working, actually. The perceptron is not powerful enough to do something very that complicated, but it inspired a lot the researcher community and the engineers. And a few years later, in 1962, nothing to do with the perceptron, but Hubel and Wiesel were two people working on the visual cortex. They wanted to know what happens in the visual cortex, in the neurons of the visual cortex when you see something. So they plugged electrodes on the brain of living cats, and they were just showing them patterns of images, different patterns, different shapes, different brightness, and so on. And they wanted to figure out what was the thing happening in the neurons. By collecting all the electrical information, the electrical data on the visual cortex, they figured out that there were some neurons very locally specialized, focused on a very local part of the image they were seeing, and those neurons were replicated all along the image. They discovered actually a lot of many things, but that's the principle of convolutional neural network. If some of you have maybe coded or designed a deep learning convolutional neural network, and this idea is the idea of the first tensors of filters that you put on the first layer of your convnet. It comes from here. Based on this work, Fukushima in 19, I'm sorry, that's not the wrong year, it's in 1980. Fukushima created the first mathematical model of the visual cortex based on Hubel and Wiesel work. The idea was to use the two principles of pooling and the simple cell and the complex cell. Actually, the visual cortex works with simple cells that react from different shape, different brightness, and there are more complex cells that can create pooling. The pooling is the idea of subsampling the image to get some information specialized locally, okay? And the more you add layer, the more you can get an information, a vector, a representation of this image that has sense or is more abstract. That was the first multi-layered artificial neural network, and a few years later, actually, Yann Lequin was a great researcher. He has done a lot in the deep learning community, in the deep learning work. And in 1988, he worked on a framework called the backpropagation framework. It's a method of optimization that makes us able to efficiently train a multi-layer neural net. The quick animation you can see on the left, trying to make a whole deep learning model learn with a fully analytic approach is very complicated. It was not even possible because you can have like maybe 10 and 100 of millions of parameters in your models. So this approach was based on the fact that there are some layers, and he found an approach based on gradient descent and chain rule formula to learn to adapt all the weights of all the different neurons layer after layer. So it is efficient, and so you can do this without having a very big computer. 2 years later, at this point, we have a model of the visual cortex. We have a technique for training model and the supervised learning, and the idea, the principle of learning. And we have Yann Lequin. The first revolution, I think, in this area happened this year when he put all of this framework, all of this research together, and succeed by to the job that to learn to make a convolutional deep neural network learn process on handwritten character recognition. It was working very well, actually. It's the first cash, bank check reader was equipped in 1995, maybe, with this kind of algorithm. That was the first machines equipped with a deep learning algorithm. But the problem was the models are very hard to train. It takes a lot of time, and there has been a lack of interest among all the community of researchers from 1995 to 2005. That was a very dark period. But obviously, in 1993, a company you might know called Nvidia was created, funded by 3 people. They got, at the first year, fundraising of 20 million by Sequoia Capital. And the idea of this company was to create a chipset that can compute all the graphic rendering without the CPU. The first graphic chipset was created in 1995. The first real GPU was created in 1999. Okay, the first 256, sorry. It was the really first graphic processor unit, but it was at first designed just to render a graphic user interface. It has nothing to do with the deep learning. But they figured out that rendering a graphic, a 2D or 3D user interface is obviously just computing some matrix multiplication, matrix sum, linear algebra operations. And that's exactly the same in deep learning. In 2007, they created CUDA. CUDA is the API that made all the researchers able to code this GPU. And the real revolution of deep learning, I think, is just about to happen in 2009, 2012. But CUDA made all the developers community able to code the GPU and to train some algorithm. A few years back, in 2003, the first project of self-driving robots was led by Yann Lequin, and it motivated another project called the Lager project, financed by the DARPA. And that initiated a lot of work about the semantic segmentation problem. Semantic segmentation is what you can see on the left, is only give to each pixel of an image a representation of the object it is representing, to see what is the road, where is the person, where is the car next to you, and so on. At this point, some companies were created, like Mobileye. They were bought by another company, I don't remember what, but the research in semantic segmentation has grown, and the community has started to take deep learning as a subject back. In 2009, Serena is the first that published a paper about training a deep learning algorithm with GPU. And all the problem that Yann Lequin couldn't answer in the 90s, because it was very too hard, too difficult to train a model, was on this paper, because the training time was 70 times faster with a GPU than CPU implementations, with the first GPU, a very old version of GPU. That made some people, Alex Krivetsky at the University of Toronto, able to train his own deep learning model. And in 2012, the ImageNet classification problem, so just so you know, ImageNet is a global challenge, or you have to train a model, whatever it is, but you have to classify images on approximately 1,000 different classes. And the score, you can see on the graph, in 2011 was around 57, so error rate around 25. And just with the AlexNet, so Alex, with the first deep learning algorithm, get an improvement of 10% compared to the older algorithms. At this point, everyone is using deep learning on the next years to solve image problem, and all the older techniques were forgot. The last thing, but not least, in 2012, we had like the research, the hardware, CUDA library, but the CUDA, to code in CUDA is very complicated. It means just something. And it happened a few years ago with TensorFlow, PyTorch, and other framework. TensorFlow was the first public framework coded in Python and C++, so widely open, and developers could create their own deep learning models. And the initial public release was done in 2015. So now you can see a lot of different applications that are emerging thanks to all of this stuff. But what appears, in fact, is that all the really important, the very interesting things happen just in the last 10 years in deep learning. But thanks to Yann Lequin and some other people that worked for 50 years now, we can do it on the garage. I mean, a developer can, in his garage, code with Nvidia RTX, the last version of GPU. He can do very amazing stuff. Thank you, and I hope you enjoyed.
Okay, first question. Can you give us perhaps a few tips about the future? Because we have seen the past. What will be the future in the next 5 years?
Yeah.
In terms of new technologies, what will be the next generation of?
Sure. In terms of hardware, Google launched the TPU, Tensor Processor Unit, so even more specialized in deep learning training algorithm. There was a paper published in 2014 by Yann Goodfellow about generative adversarial network, and according to Yann Lequin, it's the next revolution in the deep learning area. So it's a non-self-supervised method for solving some problems. The whole community, the whole research think that supervised learning will have limits because it has to be fed with a lot of data, so it can work. So I think the next research will have to be about how to train unsupervised algorithm or self-supervised algorithm to solve real-world problems, maybe. But yeah, I think GANs is the good answer.
Can you give us a few details about your company, how you guys are set up about engineering versus business?
Olivier is here as the CTO, so we split the R&D part in two parts, sorry. One for the pure deep learning science and another for the production and the product. So Olivier is responsible for the stability and the product in a general way, and we have someone from the MVA, the ENS, who is responsible only for the deep learning models performances. And we have like 5 people in the product, 3 people on the data science team, and a whole team of 15 people for now.
Okay, and about how you find the talent, do you have to hire or hunt at Google or whatever to find the best guys for your topic? How is it hard to find?
No, it's actually quite simple because I don't think there are a lot of companies that does deep learning and computer vision in a business-focused area. You know what I mean? And people love computer vision. It's graphics. They've learned it in school, at school. So we don't struggle for now for recruiting, but it might be a problem in the future because the opportunities are maybe even better at the Google or with all the competitors.
Yeah.
I'd like to ask in the specific case of Mindee, where you are trying to structure some documents, which approaches work well, what doesn't work? Something you can share? What works well? What computer vision approaches or algorithms? Maybe it's secret sauce, but.
Okay, we have benchmarked approximately all the different models of computer vision on deep learning. Do you mean you want to know the name of the models that work or the?
Yeah.
Okay. The mask-RCNN, the LinkNet, if you are interested in this. UNet, LinkNet, and mask-RCNN are very good algorithm for locating some information. So we don't want to structure actually the whole document. We just want to grab some specific information to process a workflow. So each and every of our algorithm works in 2 steps. The first step is locating the data with that kind of algorithm, and then we have a generative approach, a data generation approach to train our OCR. So 2 models, LinkNet, UNet, and then MDLSTM, for example, or I don't remember, FAN, it's the name of a paper for OCR. We can achieve actually with data generation approach performances on OCR that are above 99.5%. So the whole problem of structuring data in documents is only locating the right information at the right place.
Okay, we can move on. Thank you, Jonathan.
Thank you.